Hello everybody, and welcome to this webinar from the Global Antibiotic Research and Development Partnership, GARDP. My name is Victor Kwasi, and I'll be hosting today's webinar on building better breakpoints, data and methods needed to determine breakpoints for new agents. Revive is GARDP's education and outreach program. It aims to connect and support the antimicrobial R&D community by facilitating learning, sharing knowledge, and connecting people. These webinars are part of our educational activities. All webinars are recorded and can be viewed after the live broadcast on our website, revive.gardp.org/webinars. As always, today's presentations will be followed by a Q&A session. You can submit your questions at any time during the session via the questions window in your control panel as shown on this slide. We will address the questions after the presentation, and we'll do our best to respond to as many as possible. Today's speakers are John Turnidge and Anouk Muller, and our moderator is Gunnar Kahlmeter. Welcome, Gunnar. I now hand over to you for an introduction to this session and our speakers.
Thank you, Victor. Good morning, everyone. I hope you can hear us. Today's topics, building better breakpoints, is going to be presented by two speakers, John Turnidge and Anouk Muller. John Turnidge is a clinical professor at the University of Adelaide in Australia. And he has many publications that range from being on antimicrobials, a lot of them on breakpoint settings. So John is a real expert. He's been on CLSI and on EUCAST now since several years. And it's a great honor and pleasure to have John on board. Anouk is a clinical microbiologist in the Netherlands, in The Hague. And she's been active in the fields of pharmacokinetics and pharmacodynamics for a long time. And her expertise includes finding the best PK/PD indexes correlated to antibacterial effect. And it's a great pleasure to welcome Anouk following John's presentation. So with that, let's move on. See if I can get this slide going. Maybe you can help, Victor. Doesn't seem to be moving. Here we go. So I just want to introduce today's session with a few words on what we are talking about. We're talking about antimicrobial susceptibility testing of microorganisms such as bacteria and fungi. We are going to talk about phenotypic susceptibility testing, and phenotypic testing is based on the minimum inhibitory concentration, the MIC. Phenotypic susceptibility testing requires breakpoints, and that's really why we're here today. The nice thing about phenotypic susceptibility testing is that it predicts not only susceptibility, it also predicts resistance, it's quantifiable, and you can say things like more sensitive than, less sensitive than. And if we move on to very briefly on genotypic method, which we're not going to talk about today, they are highly specific. They will detect the gene, the resistance gene in question. They will predict resistance, but they will not, at this point in time, predict susceptibility. And they're not quantifiable. It's either or. The third method, which is often used, is susceptibility testing by deduction, or if you like, expert rules. We talk about intrinsic resistance, where we say we don't need to test. We know that this bug is always considered resistant to this antibiotic. And we say things like if and then, expert rules like if we can detect the MEK-A gene, or we can point to a phenotypic resistance against isoxazoline penicillins, then this microorganism is going to be resistant to all beta-lactams with very few exceptions. When it comes to expert rules, you need to remember that rules may change over time. They're not quantifiable, but they are very useful and part of our everyday knowledge in the laboratory. Once we have detected a MEK-A gene, we wouldn't even consider setting up susceptibility tests against certain beta-lactams. So it is very useful to know about these expert rules. They are available on the EUCAST website for anyone who is interested. Right, so next slide, Victor. When it comes to determining breakpoints, it's part of the process for registering new agents with medicines agencies' formal registration processes. And of course, we have agencies like the European Medicines Agency, the Food and Drug Administration in the US, and we have national medicines agencies in Europe working together with EMA, the European Medicines Agency. And setting breakpoints is really part of registering the agent for human use and veterinary use. In Europe, EMA has accepted EUCAST as the formal breakpoint committee, but the final say is always with EMA. So once EUCAST has suggested breakpoints following a process where EUCAST, together with EMA and with input from the pharmaceutical company, will eventually come up with proposed breakpoints, and these will then normally be accepted by EMA as the breakpoints that go into the dossier and the SMPC of the agent. So in Europe, EUCAST has this role, but EUCAST is also a technical committee that will convert MIC breakpoints into practical breakpoints for everyday testing. And that is one of the important roles of EUCAST. EUCAST also has a long tradition, reputation for interacting with clinical colleagues and microbiologists all over Europe to try to build better systems for antimicrobial susceptibility testing. Next slide, Victor. So we are going to discuss breakpoints today, and John is going to start. So I will now hand over to John, and John will then be followed by Anouk. You can pose questions via the chat, or at the end of both presentations, we will have a discussion. Thank you, and over to John.
Thank you, Victor, and thank you, Gunnar. It's my task to give you, if you like, the first half of this breakpoint setting procedures. I'm going to express my bias, the fact that this will be orientated much towards the way EUCAST does things. Fortunately, it's not a million miles from the way CLSI does things. There are some differences quite often in the way data are presented or wanted to be presented by each of those committees to make decisions. But there are many more commonalities than there are differences. So we can be happy that that if you get the gist of what you're hearing today, you'll be in a good position to know how to set breakpoints for both organisations once you've dug into the various documents on each organisation. So, Victor, I'm not getting control here, so thank you. So let me summarise my talk on here by telling you that there are 5 different areas that I wish to address. One's reference susceptibility testing. Then I want to talk about MIC distributions and epidemiological cutoff values. what in vitro models might be used to assist in setting breakpoints, what in vivo models might be used, and finally, it's the important to lead into what Anouk is going to talk about the initial PK/PD index and the targets. Then Anouk will be able to elaborate in great detail about how that very important last step works. So next slide, please. Yeah, so, whoa. Yeah, thank you. One of the really important concepts that we can't stress enough, particularly from the EUCAST point of view, is you can't really set breakpoints until you've got a reference point. It seems pretty obvious, but in fact, you'll discover that even now, today, that there are organism groups for which no reference method internationally agreed is available. Fortunately, for most common bacteria, we do have an international reference method. People often rushing off doing all these studies and saying they've used the CLSI method. Actually, what they've used is the ISO method. People should perhaps get used to the fact that, in fact, the CLSI and EUCAST reference microdilution method using cation adjusted Muller-Hinton broth in a microtiter system is the international method. It has undergone a first revision that was released last year. Probably the most important thing that happened with the revision of that document was not to methodology but to concepts. All mention of susceptible, intermediate, resistant, and any other category was removed from that document because it's actually not relevant to how the test is performed. Out of interest, there's also an ISO method that's been developed for yeasts. It's supposed to be a reference method, but in fact it incorporates both the CLSI and EUCAST methods, which do differ a little bit. So for that reason, it's not being trumpeted as a true reference method at the moment. So the second really important concept on this slide is any other way that you do the test is derivative. It's not the reference method. So you can say you did it, you know, I've done Mycobacterium tuberculosis by the BD midget system and saying, I want to set a breakpoint for that. Well, that's all very well, but that's not the reference method. That is a commercial method. So while the TB world still has continues to debate the importance of having derivative systems out there for people to use on a routine basis, they will eventually have to move into an internationally agreed reference method. The important other issues are that, or at the moment, we don't have an internationally agreed method for two important groups of pathogens, Haemophilus influenzae and its relatives, and Streptococci, for the simple reason that CLSI and EUCAST have settled on different media to do the testing. Ultimately, hopefully, there'll be a meeting of the ways in the future, but at the moment, you have to work with the methods defined by each of those standard setting organisations. Next slide. Trying it myself. Okay, thank you. So the next important concept to embrace is, having done the MIC test, is to say, what fundamental data do I need from MICs? And I'll go right to the bottom, and the bit in red, you just say, please do not give us anybody MIC 50s and 90s. Why would we say that? For the very simple reason that if half of the strains are non-wild type and half of the strains are wild type, the MIC 50 is halfway in between, and therefore isn't an indication of either the wild type or the non-wild type. So EUCAST has spent a lot of time thinking about MIC distributions, and you may or may not know, has actually set up an international MIC distribution website where you can look up MIC distributions for all sorts of antimicrobial bacterial combinations, just about everything that you can think of except the rarest of organisms. And it's also set some standards about what we should do to generate those MIC distributions and use them for the purposes of breakpoint setting, as well as for the setting of derivative tests. So here are the EUCAST criteria, which is in a standard operating procedure called SOP 10, which is available on the website. It wants data that are on scale. So if the wild type, half of the wild type are off scale at a less than or equal to value, it's called low-end truncation, and it can't, the data and the numbers can't be used effectively for breakpoint setting. And as far as the website is concerned, those kinds of data are collected, but they're hidden and are not used for setting epidemiological cutoff points. The reference method that can be used, but you can use any values from a derivative method that generate an MIC and that has been calibrated satisfactorily to this method, reference method. And there is another separate ISO standard companion document to 20776 called -2, which allows you to do that. Please know that at the moment, this document is under revision with some planned significant changes in the way the analysis is done to define what's equivalent and what's not. EUCAST also require data by species. Please don't send MIC distribution and coagulase negative staphylococci. That doesn't help anybody because we're quite sure that Staphylococcus hemolyticus and Staphylococcus aureus will have different distributions. In terms of EUCAST criteria, we require multiple labs, multiple sites and countries. And the reason that we want it that way is we want to include as much variation in the test as possible. And there is intra-laboratory variation, as you know, but there's also inter-laboratory variation, and we wish to incorporate those into the MIC distribution analysis. In order to establish an epidemiological cutoff value, or ECOFF, CLSI likes to call them ECVs, we at EUCAST wish to have at least 5 distributions. So here's some examples of them MIC distributions. These have been color-coded for our internal use at EUCAST. And as you can see, we've coded these distributions as to whether there are any particular issues. You can see a line here, Enterobacter orogenies with an orange cell. So you can see it's clearly this MIC distribution has been truncated at 0.06 milligrams per litre. And there's also other various forms of coding that are not critically important to you if you are choosing to send data, but are subsequently used for accepting distributions for inclusion in ECOFF setting or for excluding the same. As you can see, there's a second distribution in this list where the mode is clearly significantly different for that species than any mode seen by the other distributions. And so again, we believe that represents a problem and the data are excluded from the analysis. It's still collected, still stored, but they're not used directly for setting ECOFFs. So, oops, I think we went one too many there, did we? That was you and me, Victor, I think, sorry. So let me talk about epidemiological cutoff values. These are values that describe the wild type in the sense that wild type strains, those without any phenotypically detectable resistance mechanisms, and all those words are important. Finding a gene doesn't fit in here. You have to be able to find the effect of that gene phenotypically. So the wild type is strains that contain none of those phenotypically detectable resistance mechanisms. And when you see the wild type, you'll realise that it's not a single MIC, sadly, but follows a distribution itself. At EUCAST, probably more so than CLSI at the moment, we consider epidemiological cutoff values critically important, as no clinical breakpoint should be lower than an ECOFF. And I'll explain the reason for that in a moment. But the most important idea to get here is that setting a breakpoint inside the wild type will result in major issues of categorization into S, I, and R. Next slide, please. Yep, thank you. So, how do we calculate ECOFFs? I've given you the fact that we want data in a particular way at EUCAST. Well, the way that we undertake that is to use a tool that I developed many years ago based on some analytical work that Gunnar and I did many years ago. It's the Excel spreadsheet freely available on the website. Both the CLSI and EUCAST have it to set the breakpoints, but and then describe how you use this tool in the spreadsheet itself, but also within the standard operating procedure. And there's an example shown at the bottom of this slide to give you an idea of what the input, which are the bars here, which just represent the data values in the green column here, and the output once the analysis has been done by the spreadsheet. And here you would see a different number of values set for the ECOFF, and the ECOFF will be the percentage that most suits your purpose. We've discovered in recent times that the best value to start with for setting an ECOFF, once you've run it numerically through this tool, is the 99% value. Next slide, please. Okay, so next I want to, whoops, I've done it again. We've both done it. I think the delay is a bit frustrating. So we're going to move on to generating the next step in our data, and that is, this is where the pharmacodynamics start. We can use both in vitro and in vivo models, and I'll show you the common procedures without going into the details of how they all work. It just shows some examples of the output of these instruments. The simplest in vitro model is called a time kill curve, which is where you just look at killing in the test tube using fixed concentrations over a period of time, usually 24 hours. It can be quite useful, as you will see in a minute. The other models include the pharmacokinetics, so include the variation in concentrations after the drug is administered. And the two tools that are most widely used are the hollow fiber model, which is described on the left here, and the chemostat, which is described on the right. They both have their advantages and disadvantages. And these are pretty good models to be working with. They can generate an enormous amount of information. But so can time kill curves here. This is a nice picture of time kill curves where you've got 5 different antimicrobials against an organism and different concentrations in the test tube listed with those different colours there. And here you can see the profound difference between drugs where the effect is time dependent versus concentration dependent. So a time dependent drug in this setup is a drug like ampicillin, where you'll find that once you get to 2 to 4 times the MIC, no matter how much extra drug you add, you won't get any quicker or greater killing. By contrast, you can see the data here for ciprofloxacin, is that the higher the concentration, the more rapid and more profound the killing becomes. Why is that basic information useful? Well, in fact, if you know that, you can predict with some accuracy whether the drug will be a time above MIC drug or an area under the curve / peak concentration drug. And that will become obvious in a moment. So it's a good start. It's a simple experiment, and it gives you a very good guide. Certainly will take you that next step to what you might want to do in vitro models. And here's an example from a hollow fibre model, which has all the advantages in that you can simulate the in vivo PK, so the concentrations you're going to see when you administer it to man. You can study the emergence of resistance, you can study multi-day regimens, you can examine species for which there's no suitable or simple animal model, and you can examine antimicrobial combinations and variations in the ratios of those combinations. And here's the complex input. You can see the scale here has changed from hours to days. So here, the hollow fibre model has the ability to be able to track an organism like Mycobacterium tuberculosis, for instance, over a period of 28 days. The other kinds of models that are extremely widely used now for new drugs are the in vivo models, and the two most important are the neutropenic mouse thigh infection model and the neutropenic mouse pneumonia model. Both have their advantages and disadvantages, but generally speaking, we recommend that data are generated in both models because the PK/PD target values will often differ. In a sense, you're using the mouse like a machine to generate the pharmacokinetics and look for in vitro killing of bacteria in vivo. So the mouse acts as a pharmacokinetic machine, and all but the neutrophils are included as part of the inflammatory component. Do you ever use a non-neutropenic mouse? The answer is, well, you can, but for many bacteria, human pathogens, you'll have trouble growing the organism. So neutropenia is fairly standard use in these models. Next. We'll show you an example of how the mouse models look in a moment and what the critical outpoint is. But the advantages of having the mouse models are that we can include some of the other ideas that are going to become important when we administer the drug to humans. So in order to run the mouse model, you need to know the pharmacokinetics of the agent in the mouse. And if you don't think that's terribly important, that's a big mistake, because the clearance in a mouse is much higher than it is in humans. An example is the half-life of benzoyl penicillin in a human is 30 to 40 minutes. The half-life of benzoyl penicillin in a mouse is 5 minutes. So you have to know the pharmacokinetics to keep working. Secondly, you need to know about protein binding, because only free drug is active, and it can be different in a mouse from a human. So you need to work it out for the mouse. You need to induce neutropenia to minimize the white cell impact. You need to then introduce a standard inoculum to the infection site, commence a variety of dosage regimens 2 hours after it to allow the organism to settle in and start growing. And at 24 hours, the affected organs are harvested and bacterial counts are conducted of them. And here then you're able to compare the dosage regimens and the pharmacokinetics with the pharmacodynamics, which is the killing of a bacteria, against the 3 known pharmacodynamic parameters, which are percentage of free drug concentrations exceeding the MIC, or the AUC over 24 hours divided by the MIC, or the peak divided by the MIC. So those are the 3 known parameters associated with bacterial killing in vivo. And here's a nice example of how that was conducted for a single antibiotic. And the 3 different pharmacodynamic indices were plotted versus, so here's the index and its value, and here's the amount of killing observed with that particular index. And as you can see, there's a poorish relationship for Cmax and AUC-MIC ratios, but a very nice sigmoid dose-response relationship for T greater than MIC. So using modern statistical software, you just do nonlinear least squares regression to fit the curves associated with this. That then generates R-squared values, and the higher the value, the better the relationship. And in his particular example, you can see a very nice relationship with time above MIC, and you would have perhaps known ahead of time that this is a time-dependent killing drug from your time kill assays. In recent times, we've come to recognize that testing a single strain of a species, the target species, can be a problem, and you probably do need to test multiple strains to check for strain-to-strain variation, which in recent presentations we've seen for new drugs coming to EUCAST has been quite noticeable. So we would expect perhaps 5 different strains of representative species. Say it's for gram-negative organisms, we'd expect to see E. coli, Klebsiella, and Pseudomonas if it has activity against that, and 5 different strains of each in the mouse model. The other important question that's determined is, do we see, what values do we see that generate bacteriostasis, in other words, the same number of organisms we injected in the beginning, which is the dotted line in this particular graphic, and what generates 1 log kill, which here you would have seen was about down here, and here you would see that there's not a terrible amount of difference. There's a bit of a flatter curve here with this particular known model, published in 1995, showing the time-dependent drug cefotaxime, as all beta-lactams are, against streptococcus pneumonia, against Klebsiella pneumoniae in the mouse pneumonia model. Apologies. And here you can see that bacteriostasis is achieved at around 40% time above MIC, and 1 log kill is achieved at around 50% time above MIC. And these are values for later consideration in breakpoint setting that Anouk will discuss. You can also present the data for maximum kill, but at the moment, neither of the breakpoint setting, none of the breakpoint setting authorities are using that value to assist with breakpoints. And just to show you a drug that works differently, this is a concentration-dependent killing drug called colistin, and here's AUC-MIC, as therefore turned out to be the index of relevance. And here you can see that bacteriostasis is achieved with a value of that AUC-MIC of 15, and 1 log kill maybe 20 or 25 for this particular drug-bug combination. So those values are then used to assist in breakpoint setting. Finally, the PK/PD targets, and these are those values I've just shown you on the previous 2 slides, the bacteriostasis and the 1 log kill targets. Those numbers are used to assist with Monte Carlo simulations. In general, bacteriostasis is applied, targets are applied to setting breakpoints for mild infections, and 1 log kill used for more serious infections, but again, Anouk will talk more about that. And the 2 log kill or maximum kill are not used currently, and in fact, for some bug drug combinations, the mouse model will not show 2 log kill at any time. So it's not a useful target to look for. That's my last slide, and at this point, I'll hand over to Anouk. Thank you.
Thank you, John, and welcome, Anouk. We will continue directly with Anouk, just to encourage everyone to pose questions via the chat facility. So please, Anouk, take it away.
Yeah, thank you very much for your introduction, Gunnar. And I'll continue with the second part of the webinar on some different aspects on breakpoint setting. John talked about MICs and targets, and I will switch over to the more clinical part of breakpoint setting. Just go to the slide. I have to be patient, I learned. And not that patient, maybe. Victor, can you give me the next slide? Okay, there he is. Okay, well, this is an overview from all aspects that are involved in breakpoint setting. And as you can see, there are many aspects involved. And as you can see, as John talked about a few of them already, there is a preclinical part of it and there's a clinical part. But in both parts, it's very important to determine the exposure-effect relationship, and with that, the target that we're aiming at. And there are also some other aspects, and I put it in the next slide in a more colorful and easy way to talk about it. So I try to go to the next slide. Yeah, thank you very much. So this is what it's all about. In the middle, the clinical breakpoint, that's what we're aiming for. And John talked already about the green part, the distributions of the MICs, and about the orange part, how to determine the PK/PD indices and the exposure that you actually need to kill the bug. And I will focus more on the light blue part here, and that's the pharmacokinetics in human. And we'll go on. But it still one doesn't want to be quick. Yeah, thanks. So that part I'm going to talk, and then the next slide is the details, so you can go immediately to the next one. So that's the pharmacokinetics of drugs. It's important, especially when we have new drugs. We don't know anything about how the drug behaves in humans. You want to know something about how high are the concentrations that are reached, how fast is the elimination, and well, how many drugs do we have to give to patients to reach these concentrations. And we also want not only to be optimal for the average man, but also for the entire population. So it's also crucial to have information about the variability in your data. And using all those information, we're going to do some Monte Carlo simulations, as John already said, to see how the drug behaves in the population and how much drug we need to go. Okay, I have to click in the slide I just did. But it's still not working. Okay, thank you. So there are some core questions here in the pharmacokinetics. How does it behave? What concentrations are reached? And with some drugs we know, we're going to look at how the dosing regimen that are currently used in clinical practice. But for new agents, we don't know anything how it behaves. So we just starting with normally with a low dose, and we go up with the dose, and then go a single ascending dose study. and we're going to find what is needed to reach appropriate concentrations. Next slide. Okay, well, this is an example of the results of a pharmacokinetic study, and this is I will guide you through the plot. It is in the vertical axis, you see the concentrations, and on the horizontal there's time, and you see this is done in pregnant women, and they received 2 doses of amoxicillin, the first one of 2 grams and the second one of 1 gram, and you see that the concentrations is increasing and afterwards it's decreasing. And well, that's kind of logical, but it's good to see from this slide is that there is a mean concentration, but you see all the concentrations measured are scattered around the mean. So if you're going to analyze these data in a population model, you end up with a mean estimate of your clearance, of your volume distributions, and all the parameters, but also the variability. So and that is important to realize. And it's also important if you do such analysis that you are very aware of what the population is what you actually studied. So for breakpoint setting, what we're today talking about, well, I'm not expecting that you will use a population of morbid, obese, intensive care patients with burn wounds, even more complex, maybe it cannot be, but that are not the models that we're going to use. So for breakpoint setting, you choose a population what is, well, healthy volunteers or patients with mild infections, for example, patients with a pneumonia on the regular ward. So in you analyzing data, always keep in your mind, what is it, the data, what is studied? And from these analysis, you then get your clearance, your volume, and your data on your variability. Yes, but a mean value, that's very easy because you can easily do some calculations on it. But when you would determine your breakpoint on your mean value, that would result in a breakpoint for only average people. And luckily, we're all different here, so that's not good. So we have to include in some way the variability into the analysis. And that's where Monte Carlo simulations comes in hand. And that's a technique what sounds sometimes very, very difficult, but I will just explain in a few slides how it works. In general, when you do Monte Carlo simulations, you need your pharmacokinetic parameters, so your mean estimates of your clearance, your volume, as well as the data on your variability. You combine these data and you're kind of make new individuals with all the different possibilities what are in your model. So you start with a mean value of things and you end up with a bunch of possible outcomes. And these possible outcomes you compare with your target. And I know this sounds still a little bit difficult, so there's another slide here to show it in a figure. So from your pharmacokinetic analysis, you have a bunch of number of clearances. As you can see, all the colors, they're all different. And a number of values of volumes, they're all different. And you're trying to combine randomly all those possible combinations. Like you see here, it doesn't matter, you build up 5,000 new subjects randomly from all these parameters. And for all these subjects, you calculate your exposure to the antibiotic. And these exposures are compared with the targets that John was talking about in the first part of the talk. And how does that look when you do all these simulations? So this is a possible outcome of a Monte Carlo simulation. And it's a complex figure, but I'll guide you through it here. This is the Monte Carlo simulations of ceftazidime when it's dosed 3 times daily, 1,000 milligrams. And you see here on the vertical axis, you see the target. And as we know, ceftazidime is time-dependent drug. So the time above MIC is the important PK/PD index that we're looking at. So on the vertical axis, the target time above MIC. On the other side of the graph, the horizontal axis, there is the MIC distribution. Also, John talked about that in his first part of the talk. You see the concentration in this figure is going from 0.25 to 64. And you see a bunch of lines there in the graph. We'll start with the green one. The green one is the mean of the population. So this gives you information, if you look at the green line, of what you could expect for an average patient when given ceftazidime 3 times daily, 1,000 milligrams. If you look at the horizontal axis at an MIC of 0.5, you see that the target of time above MIC of 100% is reached. So you're sure that the mean patient with this dose will reach 100% time above MIC. But when the MICs are going up, you will see less time above MIC can be reached. And in the end, at 64, you cannot reach any time above MIC because it's 0. But what I said earlier is that you're not interested in only the average man, because we're setting a breakpoint. We want to be sure that you can use it for the population. So you need more than the mean person. So that's when the other lines are becoming very interesting, because that gives you information on the variability. Looking first at the orange solid lines around it, that is the 95 percentiles. So that actually means that if you're between those lines, 95% of the population, is in there. So 95% or 99%, that are the dotted lines, and that are the percentages that are used by EUCAST as the important targets. But I spoke about it's very clear that 50% is not good enough if you want to set a breakpoint, because that's only half of your population. But you can still debate on what is necessary to set a breakpoint. Is 90%, is that good enough? Or do you think then that 1 or 10 is not treated properly? Is that good enough for you? Or 95 or 99%? And if I look at all the data, breakpoint setting, it's a very, not very ill population. The model is normally used as healthy volunteers or mild infections. So I think that you should include a lot of variability and go up for the higher percentages. But it's important to realize how it works. So then we also have to talk about some clinical studies. Because they're used as well, but there are a few kind of studies that can be looked at. And this slide is the pathway of the clinical development of a new drug. And as you can see, many issues that have been shown in the previous slides are here as well. So many clinical studies are more a little bit in the end, because after we did dose finding and we did determine the concentration and the dosage that you need, then you're going to validate those regimen in a clinical trial. And these are often the non-inferiority trials, to see whether to validate what you think that is the right dose, that it's indeed working. So then for inferiority trials, the dosing regimens are often compared with a comparator drug and what's used in the clinic, and they see, well, is it good or is it even not worse than the drug that we have on the market at this day? And often that's in UTI infections, urinary tract infections, or pneumonia. To be honest, I've never seen a non-inferiority trial in brain abscesses, because that's clearly impossible. You don't have that number of patients. So there's a limited number of indications that it's used for these trials. But there are also other studies that can be done in this area to determine the PK/PD index. And I'll show you an example, and that's also on ceftazidime. And that is the data from a registration trial, the phase 3 trial of ceftobiprole. And ceftobiprole was compared to ceftazidime plus linezolid, but we took out only the ceftazidime data and looked at the gram negatives only, obvious, because that's only working, to see whether we could determine the PK/PD index in these patients. We had in total 390 patients included, of which we just throw out all the patients who did not have gram negatives in their culture. There were 170 left with MICs, and we had also many patients with MIC values of the cultures. So in a more scheduled way, you see the analysis here. The PK data in humans, we built a population PK model. We were able to calculate individual PK parameters. And on the other side, you see the culture results with MIC values, and we had individual MIC values. And we combined those two issues and come up with the individual exposure to ceftazidime. And those values were compared to the microbiological or the clinical outcome. I hope that's too fast. Yes, so here you see the results of that analysis, and of course you have very many different time above MIC values, so it is categorized per 10%, so 1 to 10, 10 to 20 are categorized, and then in that category the eradication rate has been calculated. And if you do so, you get this sigmoidal curve. Is on the vertical axis, you see the microbiological eradication rate, and on the horizontal axis, you see time above MIC. And you see that if you are treating very bad, you're doing nothing, 50% will cure anyway. So nature is mild, we always say. But it is possible to go up with your exposure and then have an increase in your microbiological eradication rate to nearly 100%. So in dosing better, optimizing your exposure, you're increasing your chance of getting cured. But then it's the question, what is the minimum value that is needed? And to see that, you can do a card analysis to differentiate between a lower and higher response rate. And in this case, the breakpoint for time above MIC needed is about 45%. And that is similar to the value what we've seen in mouse models. So that's a nice example that it's not just exposure in mice, but that we can confirm these values also in clinical patients. So now I'll try to combine all the data and aspects that we've seen in the two talks to show you how the aspects come together in breakpoint setting. And I'll again use ceftazidime as an example. And I chose two microorganisms of interest, the Klebsiella pneumoniae and the Pseudomonas aeruginosa, to see how it works. First, we're going to the green part in my overview slide. That was what John talked about. We have to know what the MICs are of these targeted microorganisms. And of course, I did not choose these two accidentally. There's a big difference between the Klebsiella and the Pseudomonas for ceftazidime. These are data you see here, the wild-type distribution that I took from the EUCAST website. You can see very nicely all the distributions over there. And if you look at the Klebsiella pneumonia here, you see that the wild-type distribution is from about 0.032 to 1.5 milligrams per liter, with an epidemiological cutoff of 0.5. For Pseudomonas, it's all higher. As you can see here, it's from 0.25 to about 8 milligrams per liter, and with an epidemiological cutoff of 8 milligrams per liter. So these are the two values that are important in the next slide. The next issue, what has been discussed also by John, is the target that we need. We know we're going to aim at the MICs of 0.5 of 8, but now we need to know how much exposure we need in patients. So we know that from often preclinical data, and here you see also from the EUCAST website, there are rational documents where a lot of information is summarized. And for ceftazidime, there's a document, and there are three targets herein. The first one is bacteriostasis. That's about 25 to 40%. well, you can probably use that for very mild infections, but for now, I think, well, we are going to look at regular infections, and then we aim, well, to have some more kill. And then here is the 2-log kill reduction, in that's 45 to 55%. And here it's stated that from clinical data, you could have a 65% of time above MIC. So from this, we know a little bit about what the range is of the target what we're aiming at. So somewhere between 45 and 65% time above MIC. So then we're going back to the plot that I showed you previously, because this summarizes also the pharmacokinetics in humans with its variability. And we're going to combine all the data that we have in here. So first, the MICs that we're looking at for the Klebsiella was 0.5, and I put it in the graph here with red lines, and for the Pseudomonas, the 8. You see that they're pretty far apart and in a different area of the graph. If we go first to look at the Klebsiella pneumonia, we see at 0.5 that it crosses the lines of the pharmacokinetics at also 100% time above MIC. And for the 8, well, that's going to be interesting if we're going to look in more detail. But first, I will show you where the target is. So the target was on the vertical axis, and we've seen from the EUCAST that we aim at about somewhere between 45 and 65%. And then we have some kill and some evidence from clinical trials. So now it's going to be interesting, and we look first at the Klebsiella pneumonia at 0.5, the epidemiological cutoff. And we look at the target and the lines that we reach in the pharmacokinetics, and we clearly show here that, well, the lines of pharmacokinetics are high. They're at 100% time above MIC. Thus, there is no issue, not for the mean, the green one, but also for the population. If you want 99% of your population adequately treated, there's no issue here at all. If we're going to look at the Pseudomonas, that's kind of a different story. Then we have to look at the MIC of 8. And if you go up from 8, from 0% time above, you see that the target area is somewhere where all those lines are different. So, well, then you have to think, well, what is exactly what I need to recommend a dose? If you would recommend only on the mean of the population, the green line, you see that the target that is reached is about going up to 60%. So maybe the mean patient can be treated with this dose. But yeah, that's not what we want. We also want the entire population. And then you're getting into troubles, because when you go down to the dotted line at 99%, it's below the target of 45%, and 45 is also the lowest of the range. So I'm not very comfortable seeing this. So I think you should conclude here that it's probably not enough for a dose of 3 times 1,000 milligrams. And that's also interesting. If you look at the breakpoints, you can see that this is truly an issue. If the breakpoint of Klebsiella pneumoniae for susceptibility is 1, so if you go up from 1, you see the time above MIC for the entire populations is 100%. So I'm not worried about that. That should be fine. For ceftazidime and the Pseudomonas, you see a very wide range here from 0.001 for susceptible. That means that there is, the result would be an I. And with the new I categories from the EUCAST and the definitions, that actually means that you should have an increased exposure to adequately treat patients and to be able to give a good result here. And that's very logical if you look at this plot. So it means that either you have to give 3 times 2 grams of ceftazidime, or you have to treat a patient with in an area with a high exposure, for example, the urinary tract If it's only need to be in the bladder, you probably have an high exposure. But you need to think about it there. The normal standard dose is not good enough to treat a Pseudomonas here. So this example shows you that all the aspects of where John talked about, the MICs, what are important, and you need to determine what exposure you need from animals, and then you have to correlate that to the pharmacokinetics in humans. What concentrations can we reach? What needs to be the dose to reach the targets that John determined in the animals, and that all these things come up to give you a clinical breakpoint in order to give the doctor a rational advice on what is, can he give, or what should not work, or what should work. So I think there are a few important messages to remember here, and that is that clinical breakpoints are really based on many factors, and that includes data on MICs, on studies in vitro, but also on human PK. So there's a bunch of data because behind the numbers in the EUCAST breakpoints tables. It's also very important that you realize that those schedules are one part of the breakpoint setting, so that if you use the breakpoints of the EUCAST, you can never use a lower dose than indicated. Higher doses are not the issue, but never give a lower dose, because then the exposure could not be good enough. And it's also good to realize that the population PK data used for breakpoint setting are, well, healthy volunteers or not very severely ill patients. So if you have a patient that is very severely ill on intensive care or morbid obese, you might have to adapt your dose and give a little bit more. And with that, I will give back the floor to Gunnar.
Thank you, Anouk. Thank you for 2 excellent talks. And we're now open for discussion. For everyone, we have about 117 participants in the webinar. I'm sure you have questions both to Anouk and John. You can post your questions via the chat. And should you have a problem with that, Victor will help you. I'm sure you'll be fine. So please submit your questions. And while you think about that, can I invite both John and Anouk to think a little bit about, let's call them difficult compartments like ELF, fluid in the lung, meninges. How can we encompass all of that in our breakpoints? Who would like to go first?
Where would you like to start?
Yeah.
Yeah, look, I think that there's an important principle here, is that when breakpoint setting organizations use it, they use all of the data that I and Anouk have talked about, including the clinical studies data. And often there's a limited number of indications, and then people start asking questions. Oh, I think I want a breakpoint for ingrown toenails, or I want a breakpoint for meningitis or something. And generally speaking, we choose not to do that if at all possible. The instruction is really work out what the right dose is for that indication that will give the necessary exposure. For instance, we saw a drug recently for which we were asked to propose breakpoints, where the initial indication said the dose was X. And then after all of the hard work that they did, both clinical and laboratory, they wanted to extend it to another indication. They realized in order to get the same exposure in that organ, they needed to double the dose. And so in the end, they were able to say the breakpoints aren't different, the exposure's the same in the organs of interest. So the response is expected to be the same, the breakpoints can be the same, But you need to know that if you're treating condition Y, you need to have double the dose than if you're treating condition X. So I think there are circumstances where we will accept setting different breakpoints. Probably the most notable is uncomplicated urinary tract infection where the drug's concentrated in urine, and responses can be expected at much higher MICs than it would be tolerated if the organism was just causing systemic disease. And I'm happy to hand over to you.
Yeah, well, I agree, of course, with you, John, and it's very important that for some indications for meningitis, we in the clinic we used to give a higher dose. That's because we know that we need a certain exposure there, and it's very hard to get into to treat the meningitis. So yeah, and for some other indications as urinary tract infections, we know that there's a high exposure. So with the I category here, then you hand it somewhat different as well. So I think it's very complex. You don't want to have too many different breakpoints for different diseases because it's not practical possible to report them all, because as a laboratory you don't know exactly what is a diagnosis, and it becomes very complicated, I think. But we know that there is, for some indications, higher doses needed.
Yes, and to add to that, if you're in the laboratory, you are presented with a problem on day 1, and you respond on day 2, and the problem is completely different at the patient level on day 3. So what started out as a rather mild infection may have turned into something much more serious by day 2 or 3. So that is a difficult concept. I think urine, as John pointed out, presents a very special compartment for the simple reason that with one of the same dose, you can reach concentrations which are so much higher than you would in any other compartment or infection site, if you like. So I think it makes sense to treat the urine and urinary tract infections slightly different than we will do other infections. Also, there are agents that are specifically suited for urinary tract infection treatment and not suited for anything else. Excellent, thank you very much, both of you, for that. I'm looking to see on the chat if Victor has moved anything along our way, but not so far. So one of the things that we've been thinking about and talking about but never done anything really about over the years is to discuss properly, when we set up our PK/PD and PK/PD indices, should they be species specific? Are PK/PD breakpoints, as it were, theoretical PK/PD breakpoints, are they automatically valid for any species and only related to the MIC, or do different species have traits that would encourage us to actually look at them separately? What about you, Anouk? Would you like to address that? Tough question.
Yeah, I think it's I think it's important if we would have a different target and breakpoint for each species, but there are some difference in PK. They react on, for example, gram positives versus gram negatives. We know that for gram negatives you need sometimes more time above MIC than for the gram positives. So I think it's important to have some distinguish between the groups, because it gets very complicated when it would be for each microorganism and each species a difference. Maybe John.
Yes, thank you, Anouk. John, do you add anything here?
Yeah, look, I think it is an important question. I mean, many people who are listening to this will realise that breakpoint setting organisations have groups called Enterobacterales or all Haemophilus or all the Streptococci or something. And we are to some extent working on the assumption that all the members in that group behave in a similar way. And I think there has been some splitting up, but we've still got all the Enterobacterales together. And to be honest, it's a pragmatic decision to keep it that way. When we start with the Enterobacterales, if we had to do all the experiments and clinical studies that were required to set it for each of the 10 common species causing serious disease in humans, that would multiply the amount of work required by a factor of 5 at least. And the question is, would that result in better outcomes for patients? At the moment, we don't have that information. So we have to take the pragmatic approach that all Enterobacterales look the same until proven otherwise. All Staphylococci look similar until proven otherwise. So eventually, when we get sophisticated diagnostic and clinical tools and we marry it all together seamlessly and automatically, we're including having measured the patient's drug exposure and in real time, then the situation can be adjusted and can change. But at the moment, the lab is stuck with the pragmatics of grouping some species in some groups.
Thank you, John. We've had a question from Anu Jain saying if one of you or both could elaborate on when a non-neutropenic model might be appropriate to use. Is there such a situation? Who would like to start?
I'm not aware of when. I know they've been published, and I know that targets in neutropenic mice are different, but I think people have stayed away from that simply because for many drugs we treat the neutropenic mouse as the kind of representative of the worst case scenario in a clinical setting. So it gives us information about the most difficult types of patients. And were we to try and set breakpoints using targets in non-neutropenic animals, I think we'd end up having a whole different set of breakpoints for a few oral drugs. And again, the pragmatics of the lab having sort all that out are real enough. And as you pointed out earlier, Gunnar, something that looks like a mild infection on day 1 becomes bacteremic on day 2 and severe sepsis on day 3. And having one breakpoint to cover all of those scenarios, you default to the worst case scenario. In other words, for sepsis.
Thank you, John.
Can I add something on that?
You've seen a few mice go by. Could you add something?
I want to add something because I think it's also important to realize what the reason is, what one of the reasons is to use the neutropenic mice. And that's also because there is a difference in the way mice react on several microorganisms than humans do. If you would, for example, use a normal mice and you would give it an infection with Staph aureus, the mice don't care at all. It just keeps running and walking and living. It's no problem. So it doesn't get an infection. So in order to make sure that there is a real infection, you have to put down the immune system. And you really want to see the response of the microorganism on the antibiotic without interference of the immune system of the mouse. There probably are microorganisms that give disease in mouse, but it can be on a different level than in humans. So if you just don't have an immune system of the mouse to be bothered by, you just know exactly the effect of the drug on the microorganism without any interference. And I think that that's quite important, because if you would give an infection and the mouse would not get a severe infection, then you would obviously need less drug. You would lower breakpoints, but that's then because of the immune system of the mouse, and it has nothing to do with the immune system of the humans.
Thank you, Anouk. I think that answers the question. There is another question here from Jennifer Smart saying, if there isn't an ISO-MIC method for the organism, the organism you are intending to study, how do you suggest we proceed with MIC determination, MIC evaluation? I think this is a question for you, John.
Yes, no, it's a very good question. And nobody's come up with a magic answer to this question yet. EUCAST would now say, well, go find a reference method and make it the reference method. But of course, you would probably have to do that outside the ISO system initially, because any process at ISO takes longer than it takes to actually develop a drug and get it into clinical practice, in our experience. It's a very long incubation period for getting additions and changes like this. So as I said, we need all of the organisations in the world involved with this to identify those gaps and come up with consensus, so that the next iteration of ISO 20776 fills in the gaps that currently exist.
I can just add to that, John, and say that if you want a breakpoint from EUCAST and there is no ISO method for your MIC determination, you ask EUCAST for advice. And if we're talking about an Haemophilus influenza, EUCAST is going to say you need to use the MHF medium, both for broth MIC determination and for if you're going to do plates. So that's an unsatisfactory answer, but it's real life. So if you want to have a EUCAST breakpoint, you need to use EUCAST guidance on how to get that breakpoint. The next question is from Anna Pereira, and this is a good one. I think this one is for you, Anouk. I know that you and Johan used to look at this a lot. When you're determining MICs and you do several repeats for a certain isolate and the results are inconsistent, which result do you consider? The highest, the lowest, or the most consistent?
Yeah, that's a very interesting question. And we have done a lot of thinking about how to handle these MICs, because, well, years ago we thought that an MIC was a very hard, good value, but now we know that there's a lot of variation in the methods and in how the drug of the microorganisms behave in the testing. So we know that if you would just measure a microorganism for 10 times, you will not get the same answer for 10 times. And that's the reason that we actually say, well, if you would do therapeutic drug monitoring, anything, we use normally the epidemiological cutoff. Also because in most routine laboratories, you don't have the gold standard method. You have someone that's derived, or that's not a real measure, but it's used in the PK/PD indices. So they normally use the highest value. That's in clinical practice, but if you go to studies and you do mice studies and you also use a value for an MIC, we always determine it for 5-6 times, and then we take the median value, and we always measure it with the gold standard method.
Thank you, Anouk. I hope everyone is satisfied with that answer. And I'm sure that everyone knows that even in the best of hands, the reproducibility of a specific MIC is at best ±1 dilution step. My experience over many years is that if you're really good at it, roughly 80 to 85% of your MICs will hit a mode, a median MIC, and roughly 15 to 20% will divide and over the MICs on both sides. So 0.5 to 2 with a mode of 1, for example. And then you take Anouk's answer and apply that to that distribution, if you like. So the next question is from Sadid Khan. And I think this is a good one. Is the choice of a 1 log kill as a bactericidal endpoint for in vivo studies a historic choice that is now accepted standard, or is there a specific reason for that choice? Who would like to address that?
You start, Anouk.
Yeah, okay. Well, I don't think it's a historic choice, or I think it's we have to look at the possibilities, and the goals you have. Obviously, when you are determining your target, you prefer kill over stasis. I think that is everyone agrees on. And for some drugs, it's not possible to get a 2 log kill. If it's possible for me, I would choose the 2 log. If that's not giving me too high doses, or if at all it's possible in your kill curves. But I think very often you end up with 1 log kill because of these reasons. But whether it's a historic choice, I don't think so. It's just, I think, the practical and possible choice.
Yes, I can perhaps add to that, Anouk. It was bacteriostasis for quite some time, but I think people started to see that it wasn't performing as well in a clinical correlate for pneumonia. But that when you applied a 1 log kill target, that pneumonia correlations looked a little better. And from pneumonia, it's gone to the situation of, well, which are the diseases which have higher morbidity and mortality? So we would add sepsis to that at least, and we often consider, what is the drug going to be used for? Is it kind of rescue when no other drug will do? You might keep pushing out beyond 1 log kill if you can get it in the test tube, or if you can get it in the mouse, because clearly you're stressing the drug as well as the patient, and you want to make sure that exposure is adequate.
Yes, thank you very much, John, and thank you, Anouk, for that. We have time for a few more questions, if my clock is not off. There's a question here regarding the probability of target attainment analysis, given the variability of MIC determinations. Interpretation for colistin in that example, and I think that this is for you, Anouk. The example referred to is the ceftazidime curve with the 0.5 and the 8. So given the variability of MIC determinations, interpretation for colistin in that example would dramatically change when an MIC of 8 is detected, but the true MIC would be 16. Which alternatives to MIC-based dosing adjustments do you see? It's a tough one.
Yeah, just I think over.
I think at an MIC of 16, I would just give up for colistin anyway. So maybe this refers to ceftazidime again.
Yeah, this is a mixture between colistin and ceftazidime, because I showed on ceftazidime, and the values I chose were the epidemiological cutoffs, so they're the highest value of the wild type distribution. So when considered a microorganism susceptible, you would suggest that everything is included. And if you go higher, you get microorganisms that are reported resistant. And if you would then dose on the measurement that you have, as Gunnar also said, you would probably add 1 or 2 dilutions to it, and then base your dosing on that value, and you can see whether you have a chance of reaching it or not from the plot.
how often, Anouk, would you say that a very simple, easy rule saying that by doubling the dose of at least a beta-lactam, you normally gain 1 dilution step, talking about MICs. Would you say that holds true most of the time?
Yeah, I think it's yeah, it holds true very often. I think there are some drugs with a more complex PK are some maybe difficult, but I think for the beta-lactams were very frequently used, that it will hold.
And I think that rhymes with the fact that most EUCAST intermediate categories for beta-lactams, at least, beta-lactams like cefotaxime, ceftazidime, ceftriaxone, etc., is usually 1 dilution wide, and the dosing for standard dosing and increased dosing is usually a doubling of the dose.
Yeah.
So it's an easy rule, but you can't trust it to hold true in every single situation. Right, so I think we have time for maybe one more question. So let me, here is one from Anu Jain. For a new drug for pneumonia, will you estimate PK/PD targets in ELF, the in vitro and in vivo models? So I think this is for you, John, then.
Yeah, no, that's a good question, actually. And in fact, I think in recent times, companies have realised that if they want pneumonia, we need to know about ELF and the exposure in ELF. And certainly EUCAST is vitally interested in having access to that information if it's available, because of the recent example I brought up. It was actually a dose X was for intra-abdominal, complicated intra-abdominal infections, and dose Y was for pneumonia. A double dose was for pneumonia, and a lot of that was driven by the fact that the exposure in ELF was only about 50% of that in other tissues, inflamed tissues. It's not mandatory to know about ELF, but actually having that information provides tremendous reassurance that if we're going for a pneumonia indication, that the dosage is correct and the breakpoints are therefore correct. I hope that answers the question.
Thank you, John. Do you want to add anything to that, Anouk, or shall we move on?
Yeah, I think it's a very complex area with the ELF, and that there is a lot of knowledge lacking from now, and because sometimes the concentrations can be very low in ELF, but the drug seems to work. So I think, yeah, it's good to have it next to the other data, but well, we need to learn a lot from it, I think.
Thank you, Anouk. Thank you, John. We're getting close to the end. I have one more last question from Laura Piddock, where she asks us to outline the key differences between EUCAST and CLSI. John, you touched on it, but could you, in a few words, sort of elaborate on the key differences, maybe the financing of the committees, the way they work, the fact that EUCAST is a little bit more real time, maybe, have more meetings every year, has the consultation process, etc. Now, I've taken all your arguments from you, but you can elaborate on some of them.
Well, yeah, those are the logistic issues. I think Laura might be wanting to hear about the fact that EUCAST is absolutely insistent that thou shalt not set a breakpoint below the wild type cutoff, below the ECOFF. And CLSI has yet to embrace that as a philosophy, so they do have.
Sorry, can I just butt in, just so there is no misunderstanding? We don't mind setting a breakpoint below the ECOFF, but we don't want to set it in the middle of the wild type. So, I mean, we have breakpoints that are actually lower than the wild type. So it's not the below the ECOFF per se, it's the fact that we don't want to set a breakpoint in the middle of the wild type.
Yeah, sorry, it's a different way of saying the same thing, but for EUCAST, as you know, it's critically important that we try to achieve that. for CLSI, quite a number of their breakpoints are currently sitting smack in the middle of the wild type. And we think that's a problem because of interlaboratory variation and assay variation, which somebody else brought up before. So it then results in those major interpretive problems that I hinted at in my talk. What other differences? The methodological ones. And I think the other things are really more commonalities than anything else. So as I said in my talk, they're not a million miles from each other at this point.
Thank you, John. And I think with that, we have reached the end of the webinar, and it's time for me to thank both speakers. Excellent talks, and I've had lots of comments over the chat saying excellent talks, both speakers. And with that, I will hand over to our host, to Victor. And thank you, Victor, for setting this up together with and for GuardP.
Thank you, Gunnar, for moderating today's session. And of course, a big thank you to John and Anouk for speaking in today's webinar. I'd like to now inform you of the next webinars we have planned. On 27th of October, Phoebe Williams and Erha Ngutsa will present their work on the medical need and regulatory challenges for developing antibiotics for children. And on 17th of November, James J. Collins, Cesar de la Fuente, Henriette Williams, and Frederick Svensson will present on discovering new antibacterials with the use of artificial intelligence. And then following this, GuardP will hold a webinar in collaboration with the World Health Organization with the title of Saving Children's Lives, Treating Neonatal Sepsis. This will be on the 20th of November, which is Universal Children's Day, and also falls in World Antibiotic Awareness Week. You can already register for these webinars on the Revive website. Please make sure to keep an eye out for our emails to stay up to date on our future webinars. So that will be all from me. I'd like to thank everybody for joining today and for contributing to this discussion. I really hope you found this webinar interesting and useful, and that you'll join us again in future. Please spread the word within your networks and encourage your colleagues to join as well. Thank you and goodbye.